Everybody, so we are on to section 6-4. This is material in something called polar graphs. And polar, just to give you a quick little informational thing, if you go to your mode, we know that on our calculator we did for years and years and years functions, right? And then we've moved into parametrics, being able to find an x and a y given a certain variable t, and did lots of stuff with that. And if we look at this third one right now, this is polar, and polar deals with basically two things. It deals with a length, or an r, and then a theta, which is an angle. So basically, how long are we going to go and how far are we going to rotate around something in order to be able to find a point. Okay, so we're going to start right here. And we're going to convert a polar coordinate, and again, a polar coordinate is anything with an r comma theta, and the theta can be in radians or in degrees. It doesn't matter which one you use, just make sure that you're comfortable with it. And rectangular means that basically like a function of a coordinate set, an x and a y. So we want to change this polar coordinate into this. So a couple different things I'm going to show you right now. So pi over 6 basically means this. So right, this is pi all the way to here, and pi over 6, that's basically 30 degrees right there, right? R is the radius, or the sometimes book refer to it as the pole, how long this pole is. So that's going to be 3. And then if that's 30 degrees, we know that this is 1.5, and this is 1.5 times the square root of 3, right? Because it's a 30, 60, 90 triangle. Now, I can also do this a couple different ways, and let me go ahead and throw that in there first. Is I believe, right, the y value is 1.5. And you know, if it was in a different quadrant, we have to take a look at the positive and negativity. And then on my calculator, I'm going to go ahead and do this. Clear this out. 1.5 times square root of 3. And I'll get 2.598. So 2.598. So a couple different things just to make sure that you guys are comfortable with how these things are matching up. So a polar coordinate says that at a given angle, pi over 6, I'm going to go out a length of 3. So when I go pi over 6 up, I go out a length of 3, it's going to take me to this coordinate right here. And if I did an x and a y coordinate, it would be those two things. And let's try something right now and watch what happens. This 3 is the r, right? So let me go to my calculator, give me mode here, and make sure I'm on radians, because I got a radian right here. So what I'm going to do is I'm going to do 3 times the cosine of that angle that we use, pi divided by 6. I hit enter, and you can see that those two numbers are the same. So what kind of cool thing here is the x is equal to r cosine theta. And then hopefully you guys will make this make sense, that the y value is equal to, you guessed it, let's do this, 3 sine pi divided by 6. Enter. And you get 1.5. So I didn't have to just know that this was a 30, 60, 90, sine. I didn't have to know that it was a 30, 60, 90 triangle, but it does make sense that it works out just the way it did. Or I could just take, if I wanted to convert from a polar to a rectangular, I do the r times the cosine of the angle to get the x, and the r times the sine of the angle to get the y. Make sure that if your angle's in radians, you use radians on your calculator. If it's in degrees, you use degrees on your calculator. Okay, so I know that there's a one-to-one correspondence here, but in reality, I can actually represent this point two ways when I'm using a polar coordinate. Okay, so you're like, what? How the heck could I do that? Well, one of you might say, well, if this is 30 degrees, can I just go 390 degrees? And the answer is yes, I could do that. So I could do a 3 comma 390, and that would take me to that same point. In fact, I guess there's an infinite number of ways if we keep wrapping it around to the right or wrapping it around to the left. But that's not what we're going to look at right now. We're going to look at the fact that we actually can do this, having the angle be 210 degrees. Angle being 210 degrees. And you're like, wait, what? 210 degrees would be like right over here, right? 210 degrees. And you're like, yep, exactly. But I'm trying to end up at this point. How do I get to this point right here, way over there, if I'm going this direction? Well, it's obvious, right? I simply am going to walk backwards. So I'm going to take off from the 210 degree angle, but I'm going to go 1, 2, 3 in the negative direction. Do we see that? So a 3, 390, a negative 3, a 210, wrapping around multiple times, or go in 180 degrees more than what your angle was, and then walking backwards. So here's my point. So a 530 and a negative 5, 210 are both equivalent polar points. And hopefully that clicks for everybody. Okay, so now let's see if we can go the other way around. Can we do a rectangular to a polar coordinate, and knowing that there's multiple polar coordinates? So let's see if I can do the little visual. So here's a 6, that's the x. Here's an 8, that's the y. So what am I looking for? I need the angle, what that is, and I need the length of that pole. Well, that should be pretty obvious on some things, that 6 squared plus 8 squared equals x squared, and so x is 10. So I know that I got a 10 for my, oops, sorry, let me do this the other way around. I got a 10 for my r. I just need to know my theta, and I can do that several different ways. I'm going to go ahead and do it in degrees, because again, my calculator doesn't give me exacts when I'm dealing with radians in a nice way. So I'm going to use tangent. So opposite is 8, adjacent is 6. So tangent inverse of that. So first off, mode. Let's go back to degrees. Hit enter. Quit. Tangent inverse of 8 divided by 6. And if I wanted to reduce to 4/3, I could have done that. I get 53.13 degrees. So 53.13 degrees. So there's one of my polar coordinates, 10 and that. Now we said that there's always 2, because I can always do a negative 10. I just need to go 180 more degrees beyond 53. So I'm going to add my calculator 180 to that, and I get 233.13 degrees. Cool. So that's being able to take a rectangular coordinate, 6, 8, and turn it into polar coordinates. So there's 2 different polar coordinates for you. Okay, so I think you got this up here before, that polar equations, we know that x is equal to r cosine theta, y is equal to r sine theta, and let me throw this one out here too, that x squared plus y squared equals r squared. These 3 things are all conversions or forms that we can help convert between rectangle and polar. So these were points or coordinates. Now we're going to talk about an equation. So r equals 6 secant theta. What the heck is r equals 6 secant theta? Well, I could go ahead and put that onto my calculator. So let's do that now, because we haven't done that yet. So the first thing I do is I go to my y equals, and you'll see that if you changed your mode a while back, I'll blow that up so that everybody can see this here. Zoom that up nicely. If you changed your mode back here to polar, and you hit your y equals, now it's an r, crazy, and I'm just going to do a couple for you. So let's do 8 sine theta, and then zoom 6 it. And you can see it's like, whoa, that's a polar. Yes, because what it's going to do, it's going to go out a distance of, what did I put again, 8 sine theta, it's going to go out a distance as it wraps around 8 times whatever the sine of theta is. And this sine starts off at 0. Sine of 0 is 0, so 8 times 0 is 0. It's going to go there. And as it gets bigger and bigger and bigger, it's going to go further. Now, if I hit zoom 5 right now, it'll make a little bit more sense, and you can see, hey, that looks like a perfect circle. Just like if I was to do this and I was to change it to cosine, I hit graph, I'm going to get a perfect circle on the x-axis. And there's all kinds of crazy stuff, and we're going to play around with those tomorrow, and you're going to see some really cool designs, or not tomorrow, but in section 6.5 on polar graphs. Some really, really cool designs that you can do with mathematics. Okay, so we said that we were going to do 6 secant theta, so we need this 6, and then secant, that's 1 over cosine, so 1 divided by cosine theta, and I'm going to go ahead and hit second insert multiplication, and there we go. I'm like, wait, what? That's a straight line up and down? Looks like, what is that? 1, 2, 3, 4, 5, 6. That's supposed to be x equals 6. That's just weird. So let's see if that matches up here. So over to here, I'm going to write out the equation. Let me blow this back up again so it's not all squishy. We know the equations r equals 6 secant theta, and this is supposed to be a line. We just graphed it. It's supposed to be a line. In fact, it's supposed to be x equals 6. So I'm going to rewrite it as r equals 6 times 1 over cosine theta. Does that make sense? Is that good? And the next thing I'm going to do is, I don't like cosine on the bottom, so I'm going to multiply by cosine theta both sides. Multiply by cosine theta both sides. So this kills this, right? And that's just a 1, so 1 times 6 is 6. Over here I got cosine theta times r, but since multiplication is commutative, I can make that r times cosine theta, right? Wait, look at that. R cosine theta is equal to x, yeah? So I can substitute that x in place of r cosine theta, and I get x equals 6, and you're like, whoa, that weird equation right there actually does equal that. And what we're going to do right now is we're going to do a few more equations from polar to rectangular, rectangular to polar, stuff like that. And let's try this one right here. This is kind of a cool one. So we got 3x plus 2y equals 12. All of you know this is a line, yes? It's a diagonal line, so let's go ahead and do this. 3x plus 2y, so let's plug 0 in for x, then y is 6. So 0, 6, 1, 2, 3, 4, 5, 6. So there's a point. Plug 0 in for y, x is 4, 1, 2, 3, 4. Got that right over there. And let's focus that again so it's better for you guys. So I know that rectangular wise, this is going to look like this. So I'm going to try and write a polar equation that will draw that line out on this little graphing calculator in the r equals format in just a second. Okay, so let's try it. So what does x equal? Well, that's r cosine theta. So I got 3 r cosine theta plus 2 r sine theta, because that's what y is, right? Yeah. Equals 12. Cool. So the goal of a polar equation, right? Polar equations right here needs to be r equals something. So I got to get r by itself. You can see on the left side of the equation I got r's on both of those things. So let's pull one of those suckers out. So r times 3 cosine theta plus 2 sine theta equals 12. Yeah, does it make sense? Well, how do I get this r by itself? Well, it's multiplying this, so let's divide by that. So r equals 12 divided by 3 cosine theta plus 2 sine theta. And it's my belief that this right here is a polar equation for that diagonal line over there. So let's give it a shot. think you can see that okay. So I go to my r equals, and I get 12 divided by, make sure you put parentheses because this is a whole big thing, 3 cosine theta plus 2 sine theta. Oh, clear, let's try that again. 12 divided by parentheses 3 cosine theta, close parentheses around your theta, plus 2 sine theta, close parentheses around your theta, and now around your denominator. Okay, cross your fingers, we're going to hit graph, and poof! Look at that. It is, you can see it goes through the, right there, at 4, right there, at 6. It is a diagonal line. Okay, so that's some basic ones. Now let's do a kind of a scarier, sketchier one right now. So we're going to try and, we know that we did circles just a few minutes ago pretty easily, right? On one of these things. We're going to try and convert this thing, really? That thing? Yes, we're going to try and convert this thing right here into a polar equation. We're going to try and graph it. Now, it's my belief, if you guys remember these things, that this format right here is a circle centered at -3, +5, with a radius that's the square root of 34, or just a little bit less than 6. Okay? So we're going to try it and see if we can do the math. And this is the only way it works out. So these x's and y's are grouped together. Right now I cannot do a square root of everything because I can't square root individual terms. But I am going to FOIL it out. So let's FOIL it out. So I get x squared plus 6x plus 9 plus y squared minus 10y plus 25 equals 34. That's just x plus 3 times x plus 3 and y minus 5 times y minus 5. I get that thing. And now I'm going to group. I'm going to group my quadratic terms, x squared plus y squared. I'm going to group my linear terms, plus 6x minus 10y, and then group my constants, 25 and 9 is 34. And yes, for those of you who are wondering, I did set this up so that this part and this part, when squared, would equal this part. It just makes it easier for us for what we're doing. Okay, so take a look at this. Look at this, x squared plus y squared. We remember, right, way over here, that adjacent, or x, or cosine, right, y, or opposite from the origin, or sine, equals hypotenuse squared, or r squared. Cool. So look at that. So I can rewrite this as r squared. I can rewrite this as 6x. So that's 6r cosine theta minus 10r sine theta. And I subtract this 34 from both sides. Subtract this 34, and I equal 0. Look at that. I got this whole big thing. I can pull an r out of both of those. Let me go ahead and do that right over here. So I get r times, because there's an r here, here, and here, right? So I can pull it out of all those things. So I can pull an r out, and I get r plus 6 cosine theta minus 10 sine theta, right? Equals 0. Well, we know based on our math that if I have something times something equals 0, then I know one of two things is true. So the first thing that could be true is that r equals 0. Yay! No, that doesn't make no sense, right? Can I get a circle whose center is at -3, 5 to have a radius or an extension of nothing? And the answer is no. So that one we can just throw out. That one's just kind of bleh. The other one would be that r plus 6 cosine theta minus 10 sine theta equals 0. So that's the other possibility, right? So if that's true, I'm going to go ahead and solve for r. which means I just need this stuff to the other side. So r equals -6 cosine theta plus 10 sine theta, just like that. Is that good? And this is going to be crazy. Watch. Here's my graphing calculator. Go to my r equals again, clear. And I believe this was -6 cosine theta, right? Close parentheses, plus 10 sine theta, close parentheses, and cross my fingers, graph. Holy crap, look at that. That's a circle. That's a circle. If you look back at the original one, we said the center would be at -3 and 5. Take a look. -3 and 5. Wow. And then the radius is square root of 34. And you can see if I drop this straight down here and straight down here, that you can see that the distance going out is going to be a little bit less than 12. So, cool. So what we've just done now is used or converted rectangular equations. Let me see that one again. Rectangular equations into a polar equation. Okay. Last thing we're going to do is we're going to look at polar coordinates and try and do this. Now again, if this was in class, we would go into some crazy problems and have some big challenges for you guys. I got to keep it as straightforward as possible because I don't get to sit with you and talk with you and see the facial expressions every day. So we're going to try and do this one right here. So boat A is at a location of 62 and 46 degrees from a certain port. Boat B is at a location of 156 and 300 degrees. So consider the 62 miles 156 miles so that we have them a little ways away. And it says, how far apart are they? And we want to know how far apart are they. Okay, so the first thing I'm going to do is I'm going to give myself a coordinate axis system. And then so boat A is at 46 degrees. When we're doing polar coordinates right here, I'm totally okay standard position wise. So 46 degrees. Remember, if it was a course or a bearing, then we want to go from due north. But here we're going to go from this. So 46 degrees. So that's approximately, right, a 45-degree angle. I'm just going to say it's that. And we're going to call this 62. And then we'll put that. And that would be boat A. Boat B is at 300 degrees. 300 degrees, remember, so this is 90, 180, 270. Ooh. That's a 30-degree angle right there, right? 300 degrees. If this is 62, 62 times 2 is 124. So I've got to make this at least double. So if that's that much, there's about double. Sorry, just realized that was off the screen. There you go. So that's about double. And then that's to 120. I got to go almost another half again. So that thing's way out there. Do you see that? Okay, so boat B is way out there. And the question is, how far is it between the two boats right now? Well, this is what I'm going to hopefully help you out with. So this is 60 degrees right here, right? If that's 30, and if that was 46 degrees, right? So I have a central angle right here of 106 degrees, 106 degrees. And this is 62, and this is 156. And I have a side angle side situation. And if I wanted to find out this side over here, I know that I can use something called the law of cosines, can't I? Awesome. So let's try it right here. X squared equals 62 squared plus 156 squared minus 2 times 62 times 156 times the cosine of 106 degrees. Got all that? So let's go ahead and put that in our handy dandy little calculator. Clear second quid. So 62 squared plus 156 squared minus 2 times 62 times 156 times the cosine of 106 degrees, close parentheses, hit enter, double check your mode, make sure it's in degrees. It is in degrees. Awesome. Go back to home screen. I get that. They are 33,511. No, that doesn't make no sense, does it? What do we got to do, right? Oh, that equals x squared, so we got to root it. So second square root, second function answer, and I get that they are 183.06 miles apart. I can answer that question. Now, one of the big things we'd have here is, let's say that if we were to extend this problem, and this is what we would do and why, because I just use a lot of cosines, and like, you didn't use the fact that they're polar in any ways or any of that kind of stuff, or the stuff we were doing before. So problem extension wise, one of the things we would do is, like, say we need to meet up, we need to get supplies from one boat to the other boat, and we're like, hey, let's meet them in the middle. So where the heck is that midpoint? Well, the dealio is I can't just split this angle, this 46 and 60 degree or 160 degree angle. I can't just split that in half and say that I'm going to go along that 53 degree mark. And the reason is because this side right here is shorter than this side right here. And only if they were isosceles would the angle bisector actually take us to the midpoint of the opposite side. So the question is, how do I find that midpoint? Well, a midpoint is a what? Midpoint is a x comma y location. So if I could get the xy location here and the xy location here for both A and B, in other words, turn my polars into rectangulars, I could probably do that. So here we go. And this is why it's so nice from what we did before. So we remember that the x and the y is magnitude times cosine of theta. So I'm going to go to my calculator here, and I'm going to do 62 cosine 46, enter. I get 43.06. I'm going to do 62 sine 46 degrees. I'm going to get 44.59. And now I'm going to do these ones down here. Same thing again. Magnitude cosine 300. So 156 cosine 300. Get a 78. And we know this is down below, right? This is down below the x-axis. So this number better be negative, right? 156 sine of 300. Enter. And you can see it's negative 135.1. Negative 135.1. We're like, hey, look at that. So how would I find the midpoint? I simply add the x's together. So 78 plus 43.06. Enter and divide by 2. 60.53. Yes. And add the y's together. 44.59 plus negative 135.1, enter, divide by 2, negative 45.25, and that is the midpoint, right? And if I did this kind of sketched out, I went about 60 out here and 45 down, you can see that that dims. That does make sense. It did. You're like, oh, man, that's still just a lot of stuff, right? Well, also, if we have these two rectangular coordinates, we could also use the distance formula between these 2 points. And guess what? If we do the distance formula between these 2 points, the square root of x2 minus x1 squared plus y2 minus y1 squared, and square root it, you know what we're going to get? We're going to get 183.06, or the exact distance between those two boats. So let's say, for instance, that boat A was going right at it, and boat B was going right at it, and they met in the middle. We know where that rectangular coordinate is, 60.53, negative 45.25. Question is, could we now say, hey, we want to send another boat from right here directly to that location, to meet them in the middle? And the answer is yes. We would just need to set up its r theta, which we can get by changing that rectangular back into a polar. And we would know how far this boat has to go out and at what angle it should leave based on the horizontal right here to get to that location. Okay, so that's a lot of stuff on polars. Hopefully this was beneficial to you in terms of all the notes and the information. Like I said, tomorrow is going to be, or section 6.5 is going to be our last thing with chapter 6, and we're going to do some really, really cool graphs. So again, this is Mr. Bells. I think I can do this like this, right? Yep, there we go. So keep working hard at this stuff, guys. Hope the videos are helping, and take care of yourself. Please, again, email me, show up at the Zoom meetings, anything that you can do to make this a little bit easier for you. Okay, we will take care and see you later.